Today we're going to take a look at our very last integration strategy that we're going to see and use. We're still going to do stuff with the integrals, but this is the last new strategy that we're going to see on how to take an integral, and it's called integration by parts. And it really comes from taking the idea of the reverse product rule. And so if you remember the product rule, if we have u times v and we wanted to take the derivative of that with respect to x, two things that are multiplied, well, that's a product, so we take the derivative of the first, or I'm sorry, we'll say the first times the derivative of the second. U times the derivative of v is dv dt dx, whatever x is, plus we take the second, v, times the derivative of the first, which is du dx. Now, I'm going to play with this a bit. We're going to multiply both sides by dx. That's the partial there that we can take out of both sides. So we get d of uv is equal to u dv plus v du. And this is really set up to take an integral of both sides. So we have the integral of 1, basically, duv, is equal to the integral of u dv plus the integral of v du. Well, the integral of 1 is just whatever variable we're integrating with, and it just so happens this is a pair of variables. So uv, if I can write it, is equal to the integral of u dv plus the integral of v du. Which seems ugly right now. I'm going to kind of move things around a bit, though. I'm going to move the uv to the other side as a positive. I'm going to switch the order here. But if I subtract the integral of v du from it, we get the integral of u dv is equal to uv minus the integral of v du. And it doesn't have to make much sense right now because we're going to look at an example of how it works. But this is the formula for what is called integration by parts. What we're going to do is we're going to have some integral. I'll copy it here in black so I can highlight various colors. Some integral that we can break up into two parts, a u and a dv. If we can break them up into those two parts, we can find their two corresponding parts, the derivative of u and the antiderivative of dv, and plug it into the formula u times v minus the integral of v du, and we will be able to solve that simpler integral. So here's what I mean by that. Let's say we want to take the integral of x e to the 5x dx. We can't use substitution on this problem because if we made u equal to 5x, du would be 5, and we have this extra x. Which we talked about a tricky way to get around it with substitution, but we're going to try a different strategy here. We're going to identify two parts to the problem, a u and a dv. Now, u is going to be the part that we can easily take derivatives of. Hopefully, ideally, we'd want this part that if we kept taking derivatives, it would go to 0. And so you might notice if we kept taking derivatives of x, we'd eventually get to 0. So that is going to be our u in this function. So u is going to be equal to the x. dv then is going to be the rest of the problem. The rest of the problem is e to the 5x dx. So it's going to be e to the 5x dx. Oops, the dx doesn't have to be in the exponent. And that represents the dv part of our equation. We need the other corresponding two pieces. We have u, we need du, which is the derivative. The derivative of x is 1. We have v, we're going to need, we have dv, we are going to need v. V is the antiderivative of dv. So we take the antiderivative of e to the 5x, and that's e to the 5x over 5. And then we can plug into this formula the integral of u, which is x, dv is e to the 5x dx, is equal to u times v. Notice we found our v. V is e to the 5x over 5. So we're going to do u is x times v, which is e to the 5x over 5, minus the integral of v, which is e to the 5x over 5. And then we see a du. Du, we'll notice, is 1. dx. There should be a dx on there. So I want to see that we've got all these elements here. We've got u, we've got v, we've got the integral of v du, all coming into this equation. What's nice now is the right side is a lot easier to take the integral of than the left side. We've got this term x e to the 5x over 5, that's already done, minus, we know the integral of e to the 5x is e to the 5x divided by 5. There's already a 5 down there, so 5 times 5 is 25. And then we always need a plus c. And we've got the integral of this stuff using our formula for integration by parts. The integral of u dv is equal to uv minus the integral of v du. This formula is a bit of a pain to work with. So I want to kind of hint at another way that we can use this same formula, but in a slightly different organization method. We're going to use what is called column integration, or tabular integration. That's another word for it. This integration method actually shows up in the great old movie Stand and Deliver. So if you want some extra homework, watch Stand and Deliver about an inner city math teacher who teaches his kids calculus. He goes over this method really briefly in the movie. They don't bring a lot of attention to it, but this is what he's doing. The way column integration is going to work is we're going to look at the problem and break it into two parts. A part that we can take a derivative of, and a part that we can take an integral of. We are going to make a column for the derivative and for the integral. Then what we'll do is we are going to go down the derivative column, and we are going to take derivatives until we get zero, if that's possible. Sometimes it won't be, and we'll talk about that a little bit later. So we'll take derivatives until we get 0, and then we will also take the same number of integrals. Then this table is going to basically tell us what our solution is. All we have to do is multiply diagonals with alternating signs. Let me show you what this looks like with the problem we just did. The integral of x e to the 5x dx. Two-part here. We want to keep our directions here. So we're going to make a column for, bring back our directions. So we're going to make a column for our derivatives and a column for integrals. We want the derivatives to ultimately go to 0, and so we're going to make the derivative column the x. So I'm going to put an x there. The integral column then is going to be the rest of the problem, the e to the 5x. E to the 5x. So you can see the problem in here is x times e to the 5x. Then what we're going to do is we can take derivatives until we get to 0. The derivative of x is 1. The derivative of 1 is 0. In the other column, then, we're going to take the same number of integrals. The integral of e to the 5x is e to the 5x divided by 5. And the integral of e to the 5x over 5 is e to the 5x divided by another 5, or 25 now. The way we're going to get our solution is we're going to multiply diagonals. So the first row times the second, and then diagonally on the next one, alternating signs. We'll always start with a plus, the next one's a minus. And so the first diagonal, you see we've got x times e to the 5x over 5, minus, the next one we've got 1 times e to the 5x over 25, add a constant, and you notice we get the exact same solution we had earlier. I think this organizes our information better, and when it works for our applications, it's going to work most of the time. This integration by parts is going to be very, very nice. So let's see if we can do this with several problems. Let's try this one. Let's take the integral of x plus 6 e to the x dx. And we'll do a column for derivatives and a column for integrals. You notice there's two parts here. There's the x plus 6 and the e to the x. The catch is e to the x, we can take an easy derivative, easy integral, but we want the derivatives to go to 0. E to the x is never going to go to 0. So for the derivative column, we're going to use x plus 6. And for the integral column, we'll use e to the x. And the derivative of x plus 6 is 1. And the derivative of 1 is 0. Then we take the same number of integrals. The integral of e to the x is e to the x. The integral of e to the x is e to the x. And then we make our diagonals. First one positive, the second one negative. So for our solution, we have x plus 6 e to the x minus 1 times e to the x is e to the x. This one we can actually simplify a little bit, so I'm going to go ahead and do that. We'll do that in orange, though. So we've got x plus 6 e to the x minus e to the x. Combine like terms on the e to the x's, we get x plus 5 e to the x for our final integral. Oh, plus c, of course. Don't forget the plus c. Let's do the integral of 3 minus x over 3 e to the x dx. Column for derivatives and a column for integrals. The derivatives that are ultimately going to go to 0 we know is 3 minus x. So the rest of it is, I'm going to call it 1/3 times e to the negative x, just to make the integral easier to work with. In fact, I'm even going to put that e to the x over 3. E to the negative x over 3. So the derivative of 3 minus x is negative 1. And the derivative of negative 1 is 0. So then we integrate the integral column, e to the negative x, and then we divide by the negative 1, so we get negative 3. And then the integral again, e to the negative x divided by the negative 1 now makes it a positive 3. And we set up our diagonals, starting with plus, alternating signs, and we end up with 3 minus x e to the negative x over a negative 3, so that's a negative term, minus, we have a negative 1, that makes it positive, e to the negative x over 3, plus c. Since we have a common denominator, let's simplify it. I'm going to make sure we take this negative through as we do it. It's not just a negative 3, but both parts have to be negative as we distribute. So we have negative 3 e to the negative x minus x e to the negative x, plus x, negative times a negative, plus x e to the negative x, plus, since we have a common denominator, we can just add e to the negative x all over 3. And when we combine the like terms, the first and last terms are both e to the negative x, we get negative 2 e to the negative x plus x e to the negative x over 3. Or if you factor out that e to the negative x, if you want, you can move it to the denominator then. 3e to the x under negative 2 plus x. Both of those are the same. Either one will work. Let's try one that gets a little more involved, but is not any more difficult. Problem number 4, then, is going to be the integral of x squared e to the 2x dx. Now, if we were to use that formula that we did at the beginning, this problem would turn into one that we would have to use the formula a second time and then simplify everything at the end. But let's look at how tabular integration, or column integration, makes this easier. We'll have a column for derivatives and a column for integrals. The x squared is eventually going to go to 0 if we keep taking derivatives. E to the 2x is really easy to take an integral of. So the derivative of x squared is 2x. The derivative of 2x is 2. And the derivative of 2 is 0. Going all the way down until we get to 0. The integral of e to the 2x is e to the 2x over 2. The integral of that is e to the 2x divided by another 2, which makes it 4. And the integral of that is e to the 2x divided by another 2, which makes it 8. Now we just, moving around here. Now we just draw our lines diagonally all the way down and alternate signs. Plus, minus, plus. So we have, for our final answer, x squared e to the 2x over 2. Then we have a minus. The second column is 2x e to the 2x over 4. Next we have a plus, and the final column is 2 e to the 2x over 8. Well, we can do a little bit of simplifying, so maybe that wasn't quite a final answer. The 2's can divide out, leaving behind a 2, and the 2's divide out, leaving behind a 4. And let's go ahead and get a common denominator just so that we can make it one fraction. We probably don't have to, but we're going to multiply everything by 2, top and bottom. 2, top and bottom. So we have 2x squared e to the 2x minus 2x e to the 2x plus e to the 2x all over 4 plus a constant. And we have our final solution. Let's take a look at one more that gets really fun before we step away from this. Number 5. Let's do the integral of x cubed plus 3x squared plus 5x minus 7 times e to the negative x dx. This would be quite an ugly problem to take the integral of. If I could get it on my screen. There we go. This would be quite an ugly problem to take the integral of if we had to do it any other way than the table. But the table makes it easy. It's going to be ugly, but easy. So the thing that we can take the derivative of easily is clearly the x cubed plus 3x squared plus 5x minus 7. The integral that's easy to take is e to the negative x. And then we'll start doing derivatives down the line. We've got 3x squared plus 6x plus 5. The derivative of that is 6x plus 6. The derivative of that is 6. And the derivative of that is 0. Integrals, we've got e to the negative x divided by negative 1 makes it negative. Integral of that is e to the negative x divided by negative 1, which makes it positive. The integral of that is e to the negative x, which makes that negative. And the integral of that is e to the negative x divided by negative 1, which makes it positive. It's long, but now we just have to do our diagonals to find our integrals, starting with a plus, then a minus, then a plus, then a minus. And so we have x cubed plus 3x squared plus 5x minus 7 times a negative, I'll make the whole thing negative, e to the negative x, minus, and then we've got a 3x squared plus 6x plus 5 e to the negative x plus, but I want to notice there is a minus there, so it's going to ultimately turn into a minus. Adding a negative is going to make it negative. We've got 6x plus 6 e to the negative x, then a minus 6 e to the negative x plus a constant, because we always remember the plus c. And this big ugly thing is our integral. And this time I'm going to skip the simplifying. Well, no, we can simplify it. That's not too bad. Let's see what happens when we simplify it. Notice when we distribute our negatives through, we're going to get a whole bunch of negatives. So the negative's going to make a bunch of things negative. Also distributing the e to the x through. So we've got negative x cubed e to the negative x minus 3x squared e to the negative x minus 5x e to the negative x plus 7 e to the negative x. Distributing the negative through and the e to the negative x through, we have minus 3x squared e to the negative x minus 6x e to the negative x minus 5 e to the negative x. Distributing the negative through and the e to the negative x, we get minus 6x e to the negative x minus 6 e to the negative x. And finally minus 6 e to the negative x plus a constant. Looking for like terms, we've only got a single x cubed here, so we've got negative x cubed e to the negative x. For x squared, e to the negative x's, we've got negative 3, negative 3, gives us a total of negative 6, x squared e to the negative x. For regular x's, we've got negative 5, negative 6, and negative 6. That's going to be negative 12 x e to the negative x. For regular e to the negative x's, we've got 7, negative 6, and negative 6. That's going to be negative 5 e to the negative x plus a constant. And since they all have an e to the negative x on them, we can bring all of those e to the x's to the denominator, and we're left with negative x cubed minus 6x squared minus 12x minus 5 plus a constant. And it has now been simplified. We now have our integral. That is a great problem. I want to address one problem, though, that we have with the table method. The table method all hinges on being able to take derivatives, 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 and ending up with 0 eventually. That's really what's going to make the table method work out beautifully. If we cannot end up with 0, we need another plan. So the question is, what if we can't get 0? Or even another question that could come up out of this is, or what if we can't integrate what we want? We look at it and say, gee, that integration really looks ugly. I can't take that integral. What do I do? Well, what we're going to do is we are going to get rid of the bad part in the derivative column. The thing that we can't integrate, the thing that we can't work with, we're going to put that in the derivative column, and we're going to take the derivative until that bad part disappears. It's gone. And then what we will use is, if we can't use a diagonal line because we're out of rows, we're going to use a straight line to signify integration. In other words, we're still going to have to do an integration step. For example, if we want to take the integral of the natural log of x dx, we don't have any way to do this, because we never had a problem where the derivative of this stuff equals the natural log. We don't know what the antiderivative is of natural log. So what we're going to do is we're going to set up a derivative column and an integral column. And we're going to put the bad part, the part we can't integrate, in the derivative column. Therefore, in the integral column, we're just going to put 1, because there's always a 1 times everything. And we're going to get rid of the bad part. The derivative of the natural log of x is 1 over x. Once we've gotten rid of the bad part, we're going to stop there. Notice if we were to keep going, we'd have negative x to the negative 2, and that would keep going, negative 3, negative 4, negative 5 power. We'd never get rid of the derivative column. It's never going to go to 0. So we just go as far as getting rid of the ugly natural log. Now in the integral column, the integral of 1 over x is x. And so we're going to have a diagonal line. But now there's no possibility for a diagonal line for the next one, so we're going to do a straight line. Still positive than negative, but the straight line means we're going to have to take an integral. So we have x, natural log of x, minus, then we have to take an integral of the product, 1 over x times x dx. So a straight line means we still need an integral, which means there's still more work to be done. Not much more work, because you notice the x's divide out. So we have x natural log of x minus the integral of dx, or 1. And that gives us x natural log of x minus the integral of 1 is x plus a constant c. And we have our integral. So a straight line means integrate this part. Let's try a few more examples. How about this one? the integral of the natural log of x over x squared dx. Again, there's no part of this where the derivative can keep being taken over and over again until the derivative equals 0. So instead, we're going to make still a derivative column and an integral column, but we'll put the ugly part that we can't take the integral of, the natural log of x. And then the integral column is going to be x to the negative 2. Taking the derivative once to get rid of the ugly stuff, now it's 1 over x. Taking the integral the same number of times makes it x to the negative 1. Divided by negative 1 makes it negative. And we do the same process with just a straight line. Positive, negative, but the straight line means we need an integral. So we've got negative natural log of x times x to the negative 1. Let's put the x to the negative 1 in front. Negative x to the negative 1 natural log of x minus, and because it's a straight line, we need an integral, 1 over x times negative x to the negative 1 dx. Well, x to the negative 1 is really just 1 over x. So what we're really saying is we have negative x to the negative 1 natural log of x. Negative times a negative makes a positive. Integral of 1 over x squared dx. Or to make it even easier to work with, that 1 over x squared becomes x to the negative 2 dx. And so when we integrate, if my colors will ever change, there we go, we get negative x to the negative 1 natural log of x. Then we have x to the negative 1. Divide by negative 1 makes it negative. Add a constant, and we have our solution. Now we might want to simplify this a little bit, taking out the x to the negative 1. That puts that in the denominator. And then we're left with negative natural log x minus 1 plus a constant. Both those answers would work just fine. Let's do one last example of this process. We're going to do the integral of x cubed natural log of x dx. Derivative column, integral column. We want the derivative of the natural log of x. That's 1 over x. We want the integral of x cubed. That is x to the 4th times 1/4. We draw a diagonal line and a horizontal line. Diagonals plus, horizontals minus. So we have x to the 4th natural log of x all over 4 minus, it's a horizontal line, so it's an integral of 1/4, which can come out of the integral, x to the 4th over x dx, which reduces to negative 1/4 times the integral of x cubed dx. Still with the x to the 4th, ln x over 4. So when we take that integral, we have x to the 4th natural log of x over 4 minus x cubed raises to x to the 4th. So we divide by another 4, and we get 1/16. Plus a constant, we have our integral. If we wanted to, we get a common denominator on this and put it all together by multiplying by 4. So we have 4x to the 4th natural log of x minus x to the 4th over 16 plus a constant. Both those answers would work just fine. So integration by parts. Two ways to attack it. One, we can use the formula, the integral of u dv equals uv minus the integral of v du. Or we can use the table method. Find a good table here. There we go. We could use the table method where we put the derivatives in one column that are going to go to 0, the integrals, so the rest of the problem in another column, Hopefully those will be easy to take integrals of. And then we alternate the signs down the diagonal to get our final solution. Take a look at the homework. This method's really easy once you try about 2 or 3 problems and get the pattern down on your own. Come to class with questions, and we will see you then.